some consequences of supersymmetry that you all probably know, but I'll remind you. And so because the Hamiltonian is Q dagger plus Q dagger Q, E has to be positive. And if you have, or 0, and if you have a ground state that has E equals 0, well, then it has to be annihilated by both Q and Q dagger. And with this particular supersymmetry algebra, the irreducible representation is either two-dimensional or one-dimensional. The ground states are one-dimensional. Everything else is two-dimensional. Because of this, there's this neat object called the Witten index that you can often compute exactly, and that gives you a lower bound on the number of ground states. And we'll come back to use that. There's some fancier stuff you can do, but that I'm not going to do today to understand the exact ground states by computing the cohomology of the operator Q. And so to give you an idea, so this is the model we spent most of our papers talking about, and not the one I'm going to talk today, but it's simple to describe, so I thought I'd tell you a little bit about that first to give you an example. So here you take Q to be an operator over any, it acts on any lattice, any dimension, any graph for that matter, and what happens is C just creates a fermion, or C dagger creates a fermion, and this extra bit just is the way we define our model. It says Q creates a fermion at any site such that all adjacent sites are unoccupied. So that's what the P. If you don't have that there, it's supersymmetric, but it's trivial. If you put this there, you get a model. And so then you just compute the Hamiltonian. It's the anti-commutator of Q dagger. And what you end up with is what in the condensed matter world they call a hopping term. All it says that if you've got a site J next to I, you can hop the particle from there to there. This is the lattice version of the usual kinetic term in a fermionic field theory. And then there's this term, which basically is a potential when you write it all out in terms of annihilation and creation operators. So that's how you can get something non-trivial that's supersymmetric. So so I said that that's another talk, but I wanted to give you a commercial for these results because I think some of them may be interesting to people who are here. So this is the greatest hits from the other papers we wrote. And in particular, one thing that has something to do with things people are talking about here is this peculiar fact that this particular model, so if you take the model I just wrote down and just described it on a one-dimensional chain, so pick my lattice to be just a string of sites, it's very closely related to the XXE spin chain at delta equals minus a half. That's the JZ over JX parameter in the spin chain. And that's antiferromagnetic. But what's peculiar is, so you get, in fact, you can use the beta ansatz. I can say that. That's so great. So you get the beta equations for this, and instead of the usual sort of e to the I PL, you get e to the I P L minus F. So L is the length of the system minus the fermion number. So there's kind of an excluded volume effect, and you find you get the exact same equations as the XXE model, except you change the length of the system to the length of the system minus the number of particles. But since supersymmetry, the way we've defined it, changes the number of particles, when you do this map to the XXE chain, the XXZ chain, this operator Q acting on the XXE chain changes the number of sites. So it's really bizarre. There was this previously unknown symmetry in the XXE chain. If you look at the XXE chain with a special boundary condition, there's degeneracies when you change the number of sites. These are the doublets, have XXE chain on different number of sites at delta equals minus a half. And this funny Q operator, which in the XXZ language is non-local, is how you change the number of sites. So that's one neat thing. You get fractionally charged excited states, which is another interesting long story. And there's been this whole industry in the mathematical physics and combinatorics communities that maybe people here are aware of. Again, this magical value of delta equals minus a half, you get neat things like if you look at the ground state wave function, it's an antiferromagnet, so it's a sum over a bunch of states, but all the coefficients of all those states are integers, and those integers have to do with combinatorial quantities like the number of alternating sign matrices. And this all comes up in this very simple to describe supersymmetric model. And for those of you who know something about conformal field theory, you can generalize this to get the rest of the minimal models. And one thing I'll point out here again, because this may be of interest in this audience, I know in this crowd it's always the ferromagnet, beta ansatz. And again, you can do the same thing for what condensed matter people usually call the TJ model, and what here might be happier if you make a spin chain with SL2/1 invariant. So it's the Heisenberg model for SL2/1. And just like the XXZ model at this delta equals -1/2 has this hidden supersymmetry, the ferromagnetic SL2/1 invariant spin chain does as well. So that's that story, and please ask me questions at the end if you want to hear more, or come talk to me later. But so now I'm going to get to what looks like a little more complicated model, but in fact is going to end up being really simple. And so here the supersymmetry acted just by creating a fermion. There were some constraints when you're allowed to do that. It just takes an empty site and puts a fermion there. So that's why it's Q is a fermionic operator. And so if you wish, you can think of that as the degrees of freedom are bosons and fermions. An empty site is a boson. The filled site is a fermion. And that was how we set up that model. So the model I'm going to set up now and devote the rest of the talk to is where you start out with things that have fractional charge. There, it's an end of the day thing. But I'll tell you how to do this explicitly in a second. But here you have Q, and Q is charge 1 in our normalization. But instead of taking a charge 0, the nothing, and making charge 1, it annihilates something of charge -1/2 and creates something of charge 1/2. And Q dagger does the reverse. And when you do this, so this model seemed a little bit crazy when we first wrote it down, but it has, it illustrates some really interesting technical issues in the beta ansatz that actually you can tell me. I'm curious if they've come up in all the beta ansatzing that has happened here. And it also tells you supersymmetry is really special. In a particle physics crowd, I don't usually need to convince people of that, but in a condensed matter crowd, I do. So I will reiterate it in any case. So like I just said, so Q creates a charge 1/2 particle while annihilates a charge -1/2. And so you can, again, concoct a variety of models to make a supersymmetric model. You just need to find a Q that squares to 0. That's actually easier said than done, but it can be done in many cases. And here's well, at least the way we thought of and the way you do it. So in fact, you think of 2 chains now. So that's one chain, and that's the other chain, and we'll couple them, you'll see, in a zigzag fashion. So that's why I drew it this way. So every site on one chain has 2 nearest neighbors on the other. And you can say some things about periodic boundary conditions, but for a variety of reasons, it's better to stick with open. So I'm going to stick with open for the day. So we just have these 2 chains coupled in this zigzag fashion. And so what we just say, any particle on this chain has charge, I forget what it was, -1/2, and those have charge +1/2. And so then what the supersymmetry operator is going to do, looks kind of funny, is it annihilates a charge -1/2 and then creates a charge 1/2. And we're imposing the specific Q we're going to look at does so on the adjacent sites if they're empty. If they're not empty, then nothing can happen. And so to make a supersymmetric model, Q has to square to 0. And the way you do this looks all ugly and horrible, but all this is just a string that basically makes Q fermionic. It makes the 2 things anti-commute when they're far away, these 2 knobs. So all you can just see, so this is annihilating one at site 2j-1, and then either creating at 2j-2 or at 2j. And again, there's this string of sort of, well, in condensed matter land called Jordan-Wigner, I don't know, Mandelstam operator, something people call it in the particle physics world. And so that's all it is. So is it clear what, so, pardon me? Fk is the fermion number of the kth site. Yeah, sorry, I probably didn't say that. So it would be -1/2 if this is filled on the bottom row, 0 if it's empty, and then 0 or +1/2 on the top row. So that's how it all works out. So those tails are ugly, but we needed those for Q. So Q is non-local, but a non-local Hamiltonian, well, maybe interesting, is pretty ugly. And so when you then take Q dagger Q plus QQ dagger to get the Hamiltonian, those tails cancel, and you get a nice local Hamiltonian. So it's broken into 2 pieces. I'll first tell you about the easy piece, this sort of free piece. So what happens is, like that first model I told you, you get a hopping term, but the fermions only hop along the chain, and that's because we have fermion number conservation, and all the fermions on one chain have one charge, and all of them on the other chain have another charge. So all they can do is hop along the same chain. There's this boundary magnetic field, which is, you'd seem to pull out of your hat if you just wrote this thing down, but to make it supersymmetric, you have to have this boundary magnetic field. Just says that you weight the energy a little bit differently if there's a particle at either end of the thing. So that's the free part. So if that were it, you could easily solve this. But the interacting part, once you just take your QQ dagger plus Q dagger Q, there's two pieces. So ignore this for a sec. I'll get back to that. But here you get a ferromagnetic interaction, meaning it's an attractive interaction between particles on adjacent sites. So that means they're on different chains. So that's the end piece here. And if you want to think in terms of spin systems, this would be ferromagnetic. The track wants to have them both filled. And then if you, so then this ugly piece there, it still looks like a hopping term, but there's some other stuff it is. But it's much easier to say in words than to look in equations. What it says is that if a particle on one chain hops by a filled site on another chain, you get a factor I. And if you go the other direction, if you hop to the left, you get a minus I. And it's the same for the particles on the other chain as well. So this model actually breaks parity. It's still, the Hamiltonian's still Hermitian, but it's parity break, and it's CP invariant, and it's time reversal. No, sorry, it's not. It's time it breaks time reversal. Yeah, sorry, I said that. It's time reversal breaking too. CPT invariant, of course. And for those people here, I don't know if there are any, but if there is anybody who like anyons in 2 plus 1 dimensions, yeah, did you? Okay, good. One person likes anyons. This is very much like what happens with anyons. With you attach a flux tube to a particle. When you bring it around, you get a phase. We're still in 1 dimension, even though we've got 2 coupled chains. But this is kind of a 1D version. Again, if anybody followed that even further, there's this whole business in the late 80s. It was very fashionable to think about anyon superconductivity. So this is a 1D anionic superconductor. Okay, I'll go back to particle physics now. So I just to say, if you want, you can think of this as a spin chain as well. So just think of filled sites as spin up and empty as spin down, and then there's some funny 3-spin this phase of I as you hop by. When you translate this into spin chain language, becomes a funny 3-spin term. But otherwise, the other terms are SC. Yeah.
I just wanted to ask about your comment about CPT. I mean, of course, this is not the Lorentz invariant theory, so is there any reason why it should be CPT invariant?
No, other than it is. I mean, you can just define, yeah.
Is it the fact that this sort of model, you can't break CPT?
Yeah, it's a good question. I mean, I was surprised. I didn't notice for months that it was even T invariant, and then I think someone made a random comment. I mean, it's sort of obvious. Again, if you think of the flux tubes, it's obviously it's T invariant because you have a magnetic field in the transverse direction. No, I don't know of any. There's some supersymmetric reason why you can never construct a supersymmetric theory like in this fashion that broke CPT, but we never thought about it. It just is. You flip the chain and simultaneously change I to minus I, and it's invariant. Okay, so now we get to the Bethe ansatz, because now it's a strongly interacting problem. In a lattice model, how do you tell strong interactions? Well, the attraction, this nearest neighbor ferromagnetic interaction between the particles has some coefficient. It's 2, I think, in our normalization. If it's not 2, you break the supersymmetry. And that's the same order of magnitude as the kinetic term, and so that means it's strongly interacting. But this one's solvable. So you can run through all the Bethe ansatz stuff. And since most people here, everyone likes the Bethe ansatz here, I'm going to give a very schematic view of what goes on, because I don't like writing down indices. If everyone doesn't know, I'll tell you. So what happens when you do the nested Bethe ansatz, you get all of these complicated equations involving these things that are sort of like particles, but they're not the real particles of the model, and often called magnons. in that context. And so you set up all that, but the equations collapse and you get free fermion momenta. And let me explain how to do that. So first I'm going to solve a model everybody could solve. I'm going to solve that model I called H-free, which is just fermions moving along a chain and then this boundary magnetic field. And the way you do that is you write down, well, there's plane wave solutions, and you have to anti-symmetrize them. So basically, we just have to sum over all these different plane wave solutions so that there's a vanishing amplitude when particles get on the same site. And so that's the answer. So you could all do that. The only slight tricky thing here is this boundary magnetic field. And what that does, instead of saying e to the I PL equals 1, it says that e to the I PL plus a half is 1. That's because we chose the boundary magnetic field to be just right. So that's elementary problem. You could give that in a undergraduate quantum mechanics class. And not you can, people do give it in an undergraduate quantum mechanics class. And the energy is, if you just work out what it is for that, it's just the sum over all momentum. This is, again, I know I'm in string theory land, but on the lattice, instead of getting p squared over 2m or whatever, you get things that look like that when you solve lattice models. So now this is a more complicated problem, though, of course, because we have these interactions, and moreover, we have two species. So the way the beta ansatz works when you have multiple species, schematically, again, I said I don't like indices, but this R is a matrix. So there, in that case, we had e to the I p PA times 2L equals 1. There's nothing here. And what this thing is, in our case, a 4x4 matrix, because it's a two-particle scattering matrix, and we have two species of particles, so therefore it's 4x4. And so what you can think of this is really a nice way to think about the beta ansatz, is that what you're doing is you're picking out a single particle, and well, if it were free, you would just take it around the world and demand that the wave function be the same. And that's how you would get e to the IPL equals 1. Well, here it has to go through all the other particles. And because of the miracle, one of the many miracles of the beta ansatz, is that you can then just get this by multiplying two particle S matrices together. That's, like I say, that's the miracle of the beta ansatz, that's possible. So what this expression is here, well, I take it around the world, but I have to go through all the other particles. And I get a bare S matrix. These are the bare, not the renormalized particles. And those all then have to give you 1. So that's schematically what's going on. That's pretty close to the reality. But because this is a matrix, now you have to solve this for the momenta, you actually then have to diagonalize these things. And that's where this word nested beta ansatz come from. So you actually have to do another beta ansatz to diagonalize this, and then you can go back and get the momenta. So it's a long story, and many people here know it. If you don't, I hope that gives you at least an idea what's going on. So here, I said at the beginning, I'm going to do open boundary conditions, which people do sometimes just because it's fun. But in this case, open boundary conditions are what give the neat results. So let me now say what happens, what you do in a beta ansatz system with open boundary conditions. So again, you start with your e to the IPL, and then you take the particle all the way to one end. And so you get the product of all these bare S matrices. Now then you bounce it off the end. And so now you've got a particle with opposite momentum, and then you bring it through all the other particles. But notice that's minus p and that's p because the particle's bounced off one wall. You bring it all the way to the other end again, and then you bring it back to where you were. So you end up with schematically what I just wrote down there. Is that clear? So that's an open beta ansatz for an open system, the generic form of that. And so again, I conveniently color-coded all these. You notice the color? So you can see what's going on there. So that's how you do the beta ansatz for a system with open boundary conditions. Of course, the R matrix has to satisfy the Yang-Baxter equation and all the other things that we need. And then there's this boundary Yang-Baxter equation, which people call the Skleanin equation sometimes. OK, so that looks even worse. So why would anyone want to do this? But here's the miracle. So if you just look at the specific answers for R, which I didn't even write out because they're ugly, but you can look in our paper and see what they are. For this particular problem I wrote down, what happens is when basically the R matrix, this bare S matrix, when you take one, flip the sign of one of the momentum, becomes the inverse of the R matrix without the momentum flipped. And there's some extra phases that come in from the boundary one. So if you go back for a second to this thing, what happens is you bounce off one wall, but as you come back, you get all R inverses, and you undo all the damage you did by putting in all these R's. You've got all these R's in there, but then you bounce off the wall, but then all these things become R inverses. So as you come back again, you undo everything. I don't know of any other examples of the Bethe ansatz where this happens, but there must be out there. If you know of any, tell me. So you undo everything, and then you bounce there. That one cancels that, and you're all done. So you end up, at the end of the day, with nothing more than what I wrote down for the free particles. That's it. So I used the word collapse, but I don't know a better word for it. Yeah?
Well, what do you mean by here? Is that
Here, this model I wrote, right. So no, it's not the delta equals minus a half. It's this model with the two coupled chains and this special interaction. So it's that, like I say, there must be more general examples of this. And I can actually kind of guess how you would construct it, but I haven't. Yeah.
Can you construct a closed chain which has some twisted boundary conditions?
You can, not that has this property. So you can do all this with that's exactly, if you want to make the model supersymmetric and put it in closed, you can do that, and you end up with a twisted boundary condition. And you end up with this ground state degeneracy I'll talk about in a bit, but not the exciting, you don't end up with this. So it may be possible, but somehow, again, it's this fact that you go around and then you undo it is what makes this work. So it really is. So this is the first case I know, well, maybe I don't know, people do open boundary conditions here, but this is the first and only case I know of where open boundary conditions are easier than periodic. Because
example, to the chain.
chain.
Open to the chain.
Is it easier?
Actually.
Okay, good. Another example. All right, so we got that equation, and so you could just say, well, we're done, but I have, how much time? I have about 13 minutes left, yeah. So that would be boring, but I made a big point of saying this model is strongly interacting. All sorts of stuff happens, but I mean, if it were just free fermions, that would be pretty weird. If you took a very complicated model, did some Bethe ansatz trickery and ended up with just free fermions, that would be just a perverse way of writing free fermions, which, wouldn't be worth anybody's time. But, I've got 15 more minutes, so I'll tell you that, in fact, the model isn't trivial. It's simple in some ways. But one thing and also when you're studying integrable models, something you start to appreciate is that just because you know all the levels doesn't mean you know the degeneracies of each level. And in particular, you have to be very careful in integrable models because there's all sorts of symmetries lurking around. And so, in fact, famous symmetries have been discovered because people have looked in integrable models and even just numerically, and you see these unexplained degeneracies in the spectrum. And then you say, well, there must be an additional symmetry there. So you learn a lot. And so just because I've told you all the levels are those of free fermions, I haven't told you how many states there are at every level. So here's, in fact, where the supersymmetry I started out this talk with can come in handy. It's because we can use the Witten index to compute at least a lower bound on the number of ground states. This actually turns out to be the exact number, but the Witten index gives this lower bound. Ask me in the question period if you don't know what the Witten index is and you want to know. Most people here probably know. So you compute the Witten index. It's really simple to do for this model. You can screw it up, but 15 minutes with this model, and you can figure out what the Witten index is. And in fact, as opposed to most models people look at that have supersymmetry, this Witten index is very strange. It grows with the size of the system. It's 2 to the L. There's our convention is there's L sites on each chain, so there's 2 L sites on these coupled 2 chains. So this is still a set of measure 0 in all the states, but it's a lot of ground states. So all those states have E equals 0. So that's what I meant when I said the degeneracies aren't the same. Obviously, in a free fermion system, you do not have 2 to the L states that have 0 energy. But what these states are, and I'll explain, so I'm telling you the answer, and I'm going to explain how we got this answer. You can get this from analyzing the beta equations. But the answer is that these things are Cooper pairs. And I think it's a general result in one dimension. If you ever have attractive interactions between fermions, we do. So you can think of each chain individually as being fermions, and then we have these attractive ferromagnetic interactions between the two kinds of the two chains. The two kinds, they have to have a pairing instability. So they have to form Cooper pairs. What's special about this model is there's lots and lots of Cooper pair states, and they're exact E equals 0 states. And so in particular, when you look at the beta equations, so the beta ansatz is deeper than the beta equations. And there was, there's a paper by Rodney Baxter explaining this in great detail about 5 years ago. If you look at the beta equations, usually they're written in the form, so I'll be schematic again. You know, e to the I PL equals something over something, where the something comes when you do all this nesting and all this other stuff. But what can happen if you have what's called an exact string solution is the denominator can be 0. But usually people don't look at that because they're not interesting or it doesn't ever happen. But if you can manage to make the denominator and the numerator 0, so that's what I meant by 0 over 0, you still find exact eigenstates of the system. And in fact, so the paper Rodney Baxter wrote maybe 5 years ago was sort of as a result of an argument with Barry McCoy. Barry made a statement that the beta ansatz was incomplete for the XXE chain when Q, the quantum group parameter, is a root of unity, the space where the quantum groups have these special representation properties. And Rodney was deeply offended, and you should all be, you're all beta ansatz aficionados, and its integrity had been challenged, that it was missing certain solutions. But see, then what goes back is, so if you write down the beta equations as something over something, you get the 0 over 0 mess. But Rodney made the astute observation that you got those equations by having this equals this, and then you divide out. And well, if this is 0, you're not allowed to divide, but there's still solution. There's still eigenstates. And it happens here, we have these exact eigenstates, but they have a very nice physical interpretation. They're Cooper pairs, because what happened when you look at these, when you look at the detailed beta equations, you see that denominator vanishes when 2 of the momenta have this relation cosine squared p equals minus cosine squared bb. So they're not, that's not, or at least one of these does not obey the free fermion condition. So one of these p's or both has to be imaginary. And these pair, each pair has 0 energy, because if you remember, the energy was the sum of cosine squared. So one of the things Baxter makes a point in that paper saying is this is a signal of degeneracies. And in fact, that's where McCoy had come in, because he was studying extended symmetry algebras, what I mentioned before. And he had observed that there were these bigger symmetry algebras. So it all fits together. When you have extra symmetries, you get degeneracies. And so the crude way of seeing this formula I have here is just put it on the computer and solve it for some system sizes and stare at the numbers. So every energy level, so you got some Hamiltonian, you diagonalize it, it spits out the eigenvectors. You see every eigenvalue basically is not only the ground state. So remember I said there's 2 to the L states that have 0 energy, but every one has some enormous exponentially growing with the size of the system degeneracies. So that's the formula there. When you stare at it for a minute, this number C is the number of Cooper pairs. And so this has something to do with the number of Cooper pairs, this 2 to the L that I talked about. So, but then the story is even a little bit more, well, even richer. And so again, let me go back to the free case. So say we had 2 free chains. We can keep that boundary magnetic field. So again, you solve it, and you get a bunch of momenta. And so since the chains are independent of each other, you just get a bunch of momentum for the first chain and a bunch of momentum for the second chain. And of course, since the chains aren't interacting, the momenta on the first chain can be the same as the momenta on the second chain. And so the rules for solving this trivial problem, let me write it out to be pedantic, is just we have some momentum so there's a bunch of integers between 1 and L since we're on the lattice and we have finite sizes. You can't take this to be whatever you want. And so just a bunch of integers. And since they're fermions on each chain, they can't occupy the same site. You can't have the same momentum on the same chain. But when they're on different chains, they can be the same. Don't have to be. And then if you just do this little combinatorial problem, you get the binomial thing to add up. And you see that gives you exactly 2 to the 2L states. And we have 2 to the 2L states in our system because each of the 2L sites can be either empty or full. So in the interacting case, we have this kind of curious thing. We know that there's these Cooper pairs, all these extra ground states, and that they don't satisfy this free particle momentum quantization condition. So I actually cheated when I wrote it down. That was assuming those other things don't happen. So these things don't satisfy that e to the IPL equals 1. And in fact, it gets even worse. You can add Cooper pairs to a state that's already there without changing the energy, since a Cooper pair has 0 energy. But there's still the same number of states as the free case. So we've got all these states that don't obey the free particle condition, but we still have the same number of states. So there has to be missing states. And so what you find then, the rules when you work on these beta equations a little more, is that you can either have for the given momenta, you have either momenta will pair into Cooper pairs, or they'll obey the free fermion condition. But then the key thing is only one particle can be of a given momentum that obeys the free fermion condition. And so even though the particle numbers on the 2 chains, which I'm calling N1 and N2, are conserved independently, and still that stays in the interaction, because remember, nothing hops from chain to chain, they still, there's still only one particle with a given momentum. So here's how you explain that awful degeneracy formula I wrote down before. Is you say the spectrum is comprised of Cooper pairs and 2 species of exclusons. So I'll tell you what that means if you haven't heard of it. So there's C Cooper pairs. So those particles are now Cooper paired, so let's ignore them. So then there's N1 plus N2 minus 2C particles that aren't paired and thus have the free fermion momentum. But those degeneracies, that formula I wrote down, and I'll show you again in a sec, can be explained by saying, well, there's, if you then say, well, here's the number of particles on chain 1, but then C of them form Cooper pairs. And so this is how many you have left, call that E1. And there's that, call those exclusons of type 1, and then those are exclusons of type 2. The other one. Then you look at this degeneracy formula. And if I rewrite in terms of that thing E, this funny, awful, weird-looking factor up in the beginning, what it becomes is just the number of ways of assigning E1 plus E2 momenta to 2 species of particles. And they're identical. So species 1 is identical with each other, and species 2 is identical with each other. And so then if you pick E1 plus E2 momenta and say E1 are going to be one species and E2, you have all these choices. And so that's that degeneracy there. And this piece then comes from there's different Cooper pair solutions that you can write down. And so why there are exclusons, why they got named exclusons a while back, is that the only way these 2 different species can interact is if one particle has momentum P, well, even if it's an excluson of type 1, then an excluson of type 2 can't have that momentum. And this is exactly what Duncan Haldane dubbed exclusion statistics. So these particles don't interact except they affect how each other fills levels. And one of his motivations was to think of how you could generalize Fermi statistics or Bose statistics or whatever statistics you like to 1 dimension, because in 1 dimension, statistics comes from when you take a particle around each other. That's why all sorts of interesting things happen in 2 dimensions. You can't take something around in 1 plus 1 dimensions. You're not allowed to go into the time dimension. And so, but then he thought, well, but the fact of how fermions fill levels, the fact that fermions only fill 1 to a level, that you can say in any dimension. And so then he was thinking about a set of integrable models called the Haldane-Shastry models. And he noticed the excitations had that property. that they obey this sort of exclusion statistic. So that's where he came from. So let's push that analogy just a little more. So then there's this symmetry he noticed there called the Yangian. And whenever you have unexplained degeneracies, what I told you a little while back was that anytime you have unexplained degeneracies, you must have some additional symmetry. So in this Haldane-Shastry chain, the symmetry is called the Yangian, which has to do with quantum groups and all sorts of neat integrable stuff. That's why it's named after Yang. But we obviously have something here, and if you just talk about exclusons and Cooper pairs, obviously you have all sorts of symmetries, all sorts of things that don't change the energy in that basis, because I can just add a Cooper pair, and that doesn't change the energy because that has net zero, so that has something to do with the symmetry. And you can actually just change different types of exclusons without changing the energy. You just change degeneracies. So this is basically where we got stuck, though, is to ask, well, what is it in this original basis, if you want to think of this as a spin model or a particle model? And that's the expression for the first non-trivial generator beyond, well, there's supersymmetry, the one I wrote down at the beginning, and then you write this horrible beast there that I won't even dwell on. It's just too horrible. And this presumably turns into some infinite dimensional symmetry algebra like the Yangian, but we don't know anything more about it than what you see on this transparency. So anyway, so good. Anyway, so to conclude, so supersymmetry is good. Particle physicists are right. And in this case, it caused a bunch of things to happen that we definitely were not expecting. And in these other models I mentioned at the beginning, all sorts of other neat stuff happens. A useful moral, since everyone here is studying the Bethe ansatz, is, the Bethe ansatz still, 75 years later, has a lot of stuff to it, and particularly 0/0 solutions. Well, and in this case, I mean, superconductivity is about Cooper pairs. So if you were to ignore the 0/0 solutions, you would ignore sort of the most interesting states in the spectrum. And then once that comes along, then you get other stuff, these exclusons. And there's an interesting algebraic question: is this some interesting new supersymmetric generalization of the Yangian? Also, the Yangian turns out generates the spectrum, so you get all the levels by doing the Yangian. You don't just explain degeneracies, you actually can generate the whole spectrum by studying the representation theory of the Yangian. And so it's a neat question to know if that happens here. And then the last sort of obvious question is, well, people study really complicated systems using the Bethe ansatz here and all over, but this, I doubt very much that this is the only time such a collapse of the nested Bethe equations happens. So please figure out another one and tell me about it. So thanks. Yeah.
A year ago, we have put a paper with Gabriele Veneziano on the net where we have found exactly the same thing coming from the planar limit of supersymmetric quantum mechanics. It turns out that this system at the infinite lambda, soft lambda limit, is equivalent to Bethe, to this Bethe chain anisymmetric with 1/2 anisotropy parameter.
Yeah, right. I mean,
it was changing length of the lattice, and this famous resume of states, they are just supersymmetric vacua.
Yeah, I think your model, from what I understood, ended up being, once you map appropriate things to appropriate things, being identical, not just equivalent, but identical to the ones. Yeah, the models I mentioned at the beginning of the talk. That's right.
On top of that, these models are also equivalent to the system of Q gas, of Q bosons, bosonic Q gas on the lattice. These are bosons which have these modified commutation rules.
Right.
So there is a third system which is equivalent.
Okay. Yeah. I knew this, but that's interesting. Yeah.
Volodya, could you please give a hint on the structure of this 4x4 R matrix? What makes it the only property you need that if you inverse one momentum, it becomes the inverse. But
yeah.
You didn't show it.
Yeah, I didn't show it because it was too ugly and it was too late last night. So I would have had to massage it into some form. So it's in the paper. So, it's very similar with some extra factors, but it's basically the same R matrix that you would get when doing the TJ model and then deforming the quantum group parameter to the value where equivalent to delta equals -1/2. So it's sort of the supersymmetric point of the TJ model. So in fact, that was how it came around to it to begin with, is that, so you take this nested TJ equations and then you basically just change the radius and you end up with this modulo some extra factors, but that's basically what it is. I don't know if that helps. The TJ model is, sorry, the SL2/1. Yeah, that's Bethe.
And the speaker again.